Hi, this is Ines Lange from University of Exeter again. In the last video, I showed you how to construct 3D models of coral colonies from overlapping photographs using the software Alizarin Metashape. In this tutorial, I now want to show you how to use these models to measure annual coral growth rates following a workflow recently published. The idea is to overlay models of the same coral colony from subsequent years, and you can then measure the distance between these point clouds, which gives you the annual extension rate. I decided to quantify slightly different metrics depending on the morphological growth form of the coral colony, and I will introduce all of them in the following, starting with branching, corymbosa, or digitoid colonies like the Socropora colony. But let's start with a blank workspace. The program I use is CloudCompare, which is freely available online. Okay, you go to Open. Navigate to the directory where you save the point clouds constructed and scaled in Alizarin Metashape. They should be in PLY format, and then choose the ones you want to compare. I will compare colony 11 in 2018 and 2019, so I always put a little 2 behind the more recent cloud. It will ask you if you want to accept these properties. Apply. Same for the other cloud. Okay, so you now have both clouds on top of each other. This one is from 2018. This one is from 2019. You can see the area is quite a bit bigger and the point density is therefore a bit lower, which shouldn't concern us too much right now. So the first thing you want to do is to align these two clouds. For first step, highlight one cloud in the menu, then go to Translate Rotate, and then you will be able to move just one of the clouds. So the right click will move it in the different directions. With left click, you can turn it, trying to get in a similar position. You can pause the transformation mode to be able to move both clouds at the same time. So tilt this a little bit more upwards and a bit closer, so it will be easy for me to compare both of them in the same window. Okay? Because the next step is to choose common points in both of the models. So you highlight both of the clouds. Got this button up here, and it will ask you again which one it will ask you which ones to use as reference. It is not very important at this point, so you just go OK. And now you can choose common points in both models. This step would be much easier if you are able to deploy permanent markers in the surroundings, for example, nails in the substrate or maybe paint points. I was not able to do this at my study site. Sometimes I'm able to use the tags as a common point, but you can see the tag moved a bit. But I will place one point on the cable tie, which shouldn't have moved that much. And then I will just look for points in the surroundings. For example, here's a borehole of a boring sponge, so I will mark this point. So you either mark these points according like in the reference cloud and the align cloud. You can also do all the ones in the reference cloud first and then the ones in the align clouds, but then you have to do it in the same order. What else? So there's a line, like a line in the substrate here. Okay, and then maybe one more on the other side of the coral colony because you kind of want an even spread around it. So this lighter spot seems to be present in both. Okay, so yeah, you want to avoid having just a line of reference points because that means these could be aligned along these points but still be tilted to either side, so you want to kind of cover it around the colony. If you're happy with that, you can also like delete single points or point pairs and then place them again. If you're happy how it looks at the moment, click Align, and then you will see how well they overlap, both the points and also the clouds. Switch it on and off. I'm happy with this for the moment. I will do it a bit more exact manually in a minute. So I click OK. Tells me it has aligned. You are able to change the point size in either of the models by going to the upper left corner, and then you can increase or decrease them, which makes it easier to see either of the clouds. Okay, I'm not perfectly happy with the fit because you can see some parts of the older colony here, which shouldn't be the case if the whole colony grew. So we'll do a bit of manual alignment. I just highlight one cloud again, go to rotate, and then shift it so it has a better fit. I can again pause to rotate both clouds, unpause to again just move one of the clouds. Okay, now the more recent cloud is coming up. So look from the other side. Go OK for now. Check again the goodness of fit by switching one of the models on and off. Now I actually think the more recent one might be placed a bit too high. So go to side view, again rotate one of them, bring it down a little bit so the surrounding area has a good fit. That's what I'm really looking at, if the surrounding is in the same level, which it is. Now you can see like the old coming through in several corners. And then if the shape of the colony is visible, it's not perfect on this side, so we'll try to rotate a little bit more. Ooh. You want both switched on so you can actually see what you do. Okay, there we are. The step seems prone to error because it's manual alignment. But when I tested the precision of this alignment step and the following measurements by repeatedly overlaying and measuring the same models, the effect on growth rates was actually very small, with like less than a millimeter standard deviation around average growth rates. Just make sure you spend some time on this to ensure good fitness, good fit. And then that is okay. All right, the next step is to segment around the border of the colonies. So you do this by, again, highlighting both of the clouds, go to little scissors. You can choose the form here. I always go with polygonal selection. And then by left clicking, you can follow the contours around the coral colony. I do it very roughly for now. The right click, you close the polygon. Then you go to segment in, because this is the area I want to keep. You can move this to the side. Unpause and then choose the areas around it more exactly. There's some down here as well. To segment out. And then on the other side, it's a bit of ruler. Segment out. Okay. For branching colonies, this doesn't have to be too perfect. The program keeps both the segmented in and segmented out area, but you can switch off the surrounding from these clouds. So you only keep the cloud segmented. We'll decrease the point size of the newer one so you can see the old one shining through. That looks good. So the next step is to compute the distance between the clouds. Make sure you select both clouds segmented and then choose this button here, compute cloud distance. It's important that you use the older one as a reference now. You can swap it otherwise. Click OK. And now it gives you an approximation, but to compute the actual distance, you have to go compute and OK. So this gives you kind of a heat map of the distance. And if you highlight the more recent cloud, which includes the scalar field, you can change between the original color and scalar field. And further down, there's a little box you can tick, which gives you the scale. So you can see the maximum distance on the branch tips up here can be up to 2 centimeters. This is always in meter because this is how you scale it in Alizarin meter shape. And then in the surrounding, there's not much difference because it's just a bit of coral tissue added. Okay. You can clearly see that branching colonies mainly grow at the branch tips. But to get actual average linear extension rates, we will measure point-point distances between the branch tips using this tool up here. First, you select both clouds, use the measurement tool, and then choose the point-point tool, which enables you to mark 2 points and then get the distance between these two. So I will choose one branch, for example this one, points. First I choose one in the upper cloud and then I'll zoom in on the branch tip and then I'll zoom in to select another one in the underlying cloud. You can check by scrolling out and twisting to see if you actually got the tips of both of them. Okay, if I'm happy and I want to keep it safe, with a right click on it you can switch on and off the X, Y and Z coordinates. And then I repeat this for at least 10 branch tips. Again, I scroll in to get a point on the cloud underneath. Yep, happy with that. Save. You have to save each of these, otherwise they disappear again, or note them down immediately. Where's the, it's a bit, zoom in, choose one in the point cloud below. That didn't work, so it does choose 2 points in the upper cloud. So go back. Okay. Oops. Right click and then save again. And I do this for at least 10 branches all over the colony. Then I note the distances. These are in meter again, so this would be 1.28 centimeters, 1.65, 1.23. I note these in an Excel sheet and then I calculate the average and standard deviation of growth for this colony. So this is the linear growth rates over time between the imaging events. As this time is usually a bit less or more than a year, remember to divide this growth by the number of days between sampling and multiply by 365. So in my case, this colony grew for 300 days. If you want to save the workspace, okay, first I go to little X to close this. You can see that the little labels are in here as well. You can switch them on or off. If you want to save the whole workspace, you have to highlight all of the layers in here. I do this by Control A and then go to Save and save it as a CloudCompare entity. Otherwise, it will only save the one layer which you highlighted. So this was my approach for branching coral colonies. If you look at massive colonies, you quantify a slightly different metric. In the beginning, you follow the same workflow of aligning the two models. This is massive varieties in 2018 and 19. You can see the 19 ones. Switch it on and off. And you also cut around the colonies, which I did here already. This time you want to be quite exact, so you can see I segmented quite exactly around the base of both colonies. Remember that you can increase or decrease the point size in the models. Now also again I will highlight both of the clouds and calculate the distance between these two. You want to make sure that the older one is the reference cloud and the more recent one is the one to compare. Okay. And again, compute. Okay. So you can see very well that growth took place in all directions, a little less here and a little more to the side. So the growth can be quite irregular. Because these massive colonies grow in all directions, you don't have to do point-point measurements as for the branching ones, but you can use the average distance of the point clouds. So in this upper panel, you can look at the histogram, which gives you the frequency of the distance between these point clouds. And if you don't go to the histogram, but to the one next to it, which fits a statistical model on the active scalar field, choose Gauss distribution. It gives you the same histogram of the frequency of distances, but it also puts on top the average and standard deviation of these distances, which translates to growth rate of this colony. So the advantage of this growth estimate from 3D models compared to coring a colony is not only that it's not invasive, but also that you look at all growth directions at once. In my paper, I called this growth radial extension because it takes place in a hemispherical fashion, but in some studies also massive growth is referred to as linear extension. Okay, so I would note this down as growth. That's it. Now for encrusting coral colonies, I combined the approaches for branching massive corals, as I assumed that they are not only growing laterally, as you can see by comparing the overlaying clouds, but also vertically to form a thicker crust. So after aligning the two models, you segment around the outline of the more recent one very carefully. Make sure you highlight both clouds to do this, even if you might switch off the older one just to be able to see the new cloud better. And now I want to quantify both radial to the sides and vertical extension. So the radial extension can be measured as the distance between the colony outlines. So if I switch off the newer one, I can define the growth as the distance between the old outline and the new one. So I again go measurements. Oh, I have to highlight the cloud first. Measurements, point measurements. And then I can, this was not exact, mark the outline and then the outline of the model, which represents the outline of the more recent one. Again, you have to click save after each one. And you do this at least 10 times around the coral colony. As you can see that the growth can also be quite irregular. Okay, across this, you can see that I measured around the coral colony, except in this spot, which was quite dark, so I might have cut a bit too far, so that's why I didn't measure here. But I tried to get a good spread over the colony. So I will again put all these values in an Excel sheet and calculate the average and standard deviation, which would be my radial extension of this coral colony. Okay, switching all these off again. To quantify vertical extension, we again highlight both of the segmented clouds. Compute the distance between these two clouds. Make sure the older one is the reference cloud. Okay. Compute. Okay. And then again highlight the more recent one in order to display the color scale. You can see this can also be a bit irregular. And again, we can put on the Gaussian model on the frequency distribution of distances, which in this case, the average is 3.6 millimeters, which I will also note down in my spreadsheet. So this is your vertical extension rate. Especially when comparing my encrusting growth rates with literature data, it was quite obvious how important the distinction between these two growth directions is. Some studies report growth rates obtained from photographs, meaning they look at radial extension, but some provide growth rates based on alizarin staining, which presents vertical growth. Yet both are just reported alongside each other in databases and papers. So it really depends what you look at. If you want to know about space occupancy, for example, looking at radial extension makes sense. But if you calculate calcification, for instance, you want to know both of these rates, yet usually these are not available. So this 3D modeling is a really elegant solution to get both of these for encrusting colonies. Well, I hope I could convince you that photogrammetry and 3D modeling is a great alternative to measure coral growth rates compared to destructive coral staining with alizarin. It works for a range of species, colony morphologies, and colony sizes, and basically only requires a camera and some basic training. I hope I could help you getting accustomed with the program CloudCompare and the workflow, and please let me know if you have any questions or comments.